Ah, Java concurrency. It's one of those topics that can make even seasoned developers a little nervous. On one hand, it's this incredibly powerful tool that lets us build the super fast, responsive apps we use every day. But on the other, it is just filled with these subtle little traps that can lead to some truly baffling bugs. So today, we're going to pull back the curtain and demystify the whole thing.
Okay, so here's our game plan. We're going to start with a quick trip back in time to see why we even need threads to begin with. Then, we'll jump into the code and see how you actually make them in Java. After that, we dive into the deep end, the shared memory model, which is where things get really interesting and complicated. We'll uncover a really sneaky bug called the visibility problem, and finally, we'll look at the magic keywords that come to our rescue.
First up, let's set the stage. Because to really get a handle on multi-threading, you kind of have to understand the whole journey of how computers got here, from doing one simple thing at a time to the juggling act they perform today.
Way back in the day, computers were, well, pretty basic. One CPU, one job. That's it. Then we got multitasking, which was a clever trick. It created the illusion of doing many things at once by having the CPU switch between programs super fast. But today, with multi-core processors and everything, we've got the real deal. True parallelism, where multiple threads inside a single application can actually run at the exact same time on different CPUs.
So this is the key difference you got to remember. Multitasking is about the operating system juggling whole programs, like your browser, your code editor, and your music app. Multi-threading is way more granular. It's about juggling all the little tasks inside just one of those apps, which is what makes them feel so snappy and responsive. Now, this power to run things in parallel is amazing. It gives us incredible performance. But it's a double-edged sword. It opens up this whole Pandora's box of weird problems. Because when you have multiple threads all trying to read and write to the same piece of data at the same time, well, that's when you get chaos. We're talking corrupted data, frozen applications, and all sorts of synchronization nightmares. Okay, enough theory. Let's get our hands dirty and look at some code. We know why we need threads, but how do we actually, create one in Java? Turns out there's the old way, and then there's the much better modern way.
The original method, the old school way, was to just make a new class that extends Java's thread class. You'd stick all your code in the run method, create an object, and hit start. It's simple for sure, but it's also pretty rigid.
And hey, don't just take my word for it. As our source material from Coding with Amon points out, this whole approach is considered legacy. It's just not how you'd want to write concurrent code today in a modern application.
The way we do it now is so much cleaner. You separate the what from the how. You define the task you want to run as a runnable. And these days, you'd probably use a slick Lambda expression for that. Then you just hand that task over to a brand new thread object and tell it to run. It's way more flexible and just leads to better code.
Oh, and it's also worth knowing about these things called daemon threads. Think of them as the background crew. They're perfect for jobs like logging or garbage collection, stuff that needs to happen but you don't want it to hold up the main show. The key thing is, the application won't wait for them to finish before it shuts down.
All right, so we've made our threads, they're off and running. And now we get to the absolute heart of the matter, the shared memory model. This is the meeting point for all our threads, and it is precisely where all the really tricky concurrency problems start.
So remember, all our Java code lives and breathes inside something called the Java Virtual Machine, or JVM. The JVM is like the universe for our application. It manages everything, especially memory. And it has a very specific set of rules for how it's all organized.
And this brings us to this really crucial split in how memory works. Every single thread gets its own private little workspace called a stack. This is for its local variables, and it's totally safe and isolated. But all the objects, they live together in one giant shared space called the heap. You can think of the heap as the public town square where all the threads can meet and interact.
And right here, this is it. This is the central challenge of concurrency. You can have 2, 10, even 100 different threads all holding a pointer to the exact same object in that shared heap. This means they can all read it and they can all try to change it, sometimes at the very same instant. You can see how this might get messy.
And just when you thought it was complicated enough, there's another layer, the hardware itself. To make things faster, each CPU core has its own tiny, lightning-fast memory called a cache. It keeps a local copy of data from the main memory, or RAM, because RAM is actually pretty slow in comparison. This is fantastic for performance, but it creates a massive communication problem for threads running on different cores.
Yeah, that gap between what's in a CPU's private little cache and what's in the shared main memory, it leads us directly to one of the most evil, hard-to-find concurrency bugs there is, the visibility problem.
It really forces you to ask this critical question, right? What happens when a thread running on core 1 changes a value, but that change is only saved in its own private local cache? What does a thread running on core 2 see? Does it see the new value? The old one?
Let me paint you a picture. Imagine thread 1 does some work and then sets a flag to true. This is supposed to be the signal for thread 2 to stop waiting. But look what happens. Thread 1 finishes, it sets the flag, and thread 2 is totally clueless. It never sees the update, so it's now trapped in an infinite loop, just spinning forever.
So why does this happen? Well, that updated true value from thread 1 is basically trapped in its CPU's private cache. It never got flushed back to the shared main memory. So when thread 2 goes to check the flag, it just keeps reading the old stale false value over and over again. And that, right there, is the visibility problem in a nutshell.
So, our app is totally frozen, all because our threads are basically giving each other the silent treatment. How on earth do we fix this? Well, thankfully, Java gives us some special keywords that act like traffic cops, forcing our threads to communicate properly.
And for this particular nightmare, the solution is, believe it or not, almost laughably simple. All we have to do is add one single keyword, volatile, to our flags declaration, and the problem completely disappears.
See, the volatile keyword is basically a direct command to the JVM. It says, listen, this variable is special. Don't ever trust a cached copy of it. Every single time a thread wants to read it, go directly to main memory. And every time a thread writes to it, write it back to main memory immediately. It's a guarantee that every thread will always see the most up-to-date value.
Now, there is another tool in our toolbox, the synchronized keyword. Its main job is to act like a lock on a door, making sure only one thread can be in a certain block of code at a time. But as a side effect, it also guarantees memory visibility. When a thread leaves a synchronized block, it's forced to flush all of its changes back to main memory for everyone else to see.
And that really brings us to the core of it all. Multi-threading is absolutely essential for building high-performance, modern software. There's no getting around it. But that incredible power comes with a price. It demands that you understand how threads, memory, and the hardware all interact, otherwise you'll fall into these subtle, disastrous traps. The power is immense, but so is the responsibility.